All right, folks, we'll go ahead and get started. Pick up back on chapter 2 where we left off. Okay, so this is a bit of a calculator practice. Did everybody have their calculators?
No, not yet.
No? Okay. That's okay. We'll go ahead and kind of just skip this for now.
Okay.
What I would recommend, though, is that seriously practice with the calculator you're going to be using for the exams. Okay? Use that on the homeworks. Don't go and use your computer and your phone for all the stuff that you do at home, and then suddenly try to use a calculator that you've never used before on the exam. Okay? Because it is a tool, right? Anybody ever hammered stuff in?
Yeah.
What happened the first time you used a hammer? You either hit the stuff not that you weren't trying to hammer, or you hit your own fingers, right? So same thing happens to the calculator. You're going to hit all sorts of stuff you didn't want to hit, and it's going to be a problem. Okay? So practice with that calculator you're going to use. So here we see a calculator display. We do this in the calculator, and we see that these numbers have significant figures. When we type this into the calculator, you should never round except for when you're doing your final answer. Okay? Just keep as many digits as you can each time. If you know how to use your calculator well, you never have to round. You can just keep using that same number over and over, right? You can even store the number and recall it later if you need. Okay? However, if you are having issues with your calculator, if you don't know how to store the numbers on your calculator, if you want to have a backup that you write out, go ahead and write out basically 3 sig figs more than your max. Okay? So in this case, I'd recommend writing something out that would be like 6, 7 sig figs, right? And then you'd use all of those to do the calculations, and then you would go to the minimum number of sig figs at the end. And that's where you'd start rounding things down. Okay? If you do that, then your error is going to be, when you do these calculations, way lower, and you're going to have a lot less issues, okay? Okay. All right, so we go ahead and plug these numbers in our calculator. We get this displayed. Did plugging those numbers in our calculator make these numbers more certain? Somehow better measured? No. And so this is sort of an error that's really, really common. Unfortunately, it's even really, really common in like PhDs in physics. I don't know how many publications I've had to send back because a physicist thought that because they did their calculations super well, they now have 5 extra sig figs than the measured values that they generated their numbers from. Okay? Very, very common. In fact, smartest guy I ever knew, Peter Groner, really smart guy, really cool guy, very friendly actually. He used to go to conferences, and people from all around the world would literally follow him around from conference venue to conference venue, asking him, hey, could you figure out this thing that we can't figure out? And he would. Sometimes right there, like 10 minutes between the conference. That's your problem. That's been holding up my research for a year. Brilliant. We used to have to always go down and double check on him because we'd give him data, and then he'd be trying to fit something 20 digits down from where our error is. And so he'd spend months trying to perfectly fit this data 20 decimals down. And it's only good to the hundredths place in the decimals. It would be like guesstimating, I think the ceiling's probably what, 15 feet? And then I start doing calculations, and I try to fit that ceiling height prediction down to like the 10th decimal place, right? Doesn't make any sense, does it? So it's something that you see a lot, and I'm going to try to train Navi right here and right now. Okay? So it's always the minimum number of significant figures that are actually applicable, right? An easy way to think about this is if this was 0.9, that would change numbers over here, wouldn't it? any number below that becomes meaningless if that number was actually wrong, right? Yeah, which it is. It's a little wrong, okay? And so every number beyond that point, totally meaningless. That error completely overwhelms them. Yeah, junk. Okay, and so this number, you would get this in the calculator, you'd round it down because this number right here is below 5, right? And that would give you 2 sig figs, 5.4. All right, so let's go ahead and look at this. We have 3 sig fig numbers on both of these. 8 divided by 2. We get 4 on the calculator. Why in the world did we get 4? Is that the right number?
Yes.
Yeah.
Kinda.
It's missing the significant figures, but it's the correct number.
Yeah, so it's the correct, 4 is correct, but 4.00 is the actual real number, right? Yeah, because we didn't lose any accuracy in this. We didn't lose that certainty, okay? And again, this is really because of how calculators work. Like every calculation is programmed in, right? And so programming in sig figs would have been a much, much, much more difficult thing whenever they made calculators, and they did not do that. In fact, HP has, if you look up HP and calculator errors, there's actually a really fascinating story about they messed up on their calculator. There was a function on their calculator that was wrong for almost 30 years. You can still find them. Yeah. So let's perform the following calculation of measured numbers. Let's give the answer with the correct number of significant figures. So we have 5 centimeters times 3.408 centimeters divided by 2.0 centimeters. Okay. So go ahead and try to get that calculated.
How do you
Make
know
a
how
real
many
attempt on it.
sig figs you need?
You always take the least number of sig figs. So this one's going to be 2 sig figs here. That's 3, that's 4. And so we'll end up taking 2 sig figs. Okay. 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 And so what do we got?
8.5.
Very good. Excellent. Yeah, we would have gotten 8.52 out on our calculator, right? But we need to round that one down to sig figs. And so we end up in those 2 sig figs. Okay. All right, so let's go ahead and talk about addition and subtraction with sig figs. Now, when we're talking about multiplication, if I multiply my bank account by 0.0001, am I going to be happy?
You're gonna get like
Yeah, I'm going to have nothing left in my account, right? Because when I multiply by a small number, it ends up becoming a small number, isn't it? Now, if I multiply by a really big number, it becomes a really big number, right? And so it's the number of digits that we have to worry about for sig figs when we're talking about multiplications, right? Or divisions, for that matter. Now, when we do additions, if I add a hundredth of a penny to my bank account, will I care? No, I won't, will I? What if I subtract a hundredth of a penny from my bank account?
probably not gonna notice.
No. And in fact, the bank does that all the time. Everybody knows that, right? So in a chain of transactions, they actually round that transaction number down to the pennies, and they always round down and keep the extra. Which is pretty freaking crooked, right? But interesting little factoid, there's been 3 times in the history of the US that people have designed viruses to do that. And so they infected various different financial instruments, and then they rounded down just like the bank would, and then put that money into an account. The last time I remember, and I'm aware of, happened with a Ukrainian, I think it was, but they never really figured out if it was Ukrainian or Russian, hacker group. And they stole, when they disappeared, it had been worth $100 million. But it actually kept accruing money because they didn't get it stomped out right away. And they ended up stealing a total of $400 million. And that was over a fairly short period of time that they did that. So, excuse me, addition, subtractions, you don't notice those extra digits, right? It's not as important. And so when we look at this number right here, if we do a bit of an addition, we have a 2.012. Apparently my offsets got messed up when I transferred. Let's see if I can fix those. Those look even? Okay. Oh, those look for all of you. Period about the same place? Okay. Okay. So here we see that this goes all the way down to the thousands place, right? This one goes all the way down to the hundreds place. This one goes down to the tenths place. Notice that this one would only be 2 sig figs, but the sig figs don't really matter in this case, okay? Our sig figs are going to change, and that's because the addition and subtraction rules, it depends on how big the number is, doesn't it? Yeah. So the largest uncertainty, the one that's in the tenths place here, is going to overwhelm everything else. Because any change in this digit means these digits are pointless. Okay? And that's always sort of the thing you want to keep in the back of your head when you're dealing with sig figs, is ultimately they're uncertainties, right? That's what you're doing. Okay. Okay, and so we go ahead and add these together. The calculator is going to display this number right here. But what we can see is that the uncertainty is right here. In reality, this number here is not 3.0. It's something that rounds to 3.0, and we can't really tell exactly what it is. Okay? And so that last digit, if we started measuring better, it might be a 3.1, right? Maybe. We just couldn't tell. And so again, these are meaningless. They don't actually give us any information. And so we end up with a tenths place here. Now keep in mind that sig figs do not matter. For example, this is 2 sig figs here. That's the lowest number of sig figs. We are magically 3 sig figs now. Okay? And that's just addition and subtraction. Okay? All right. Right here, subtraction. Again, we have a hundredths place here. We have a tenths place here. And so we're going to round to the tenths place. Because any change in that tenths place makes everything else meaningless, right? And so calculator gives us this. We go ahead and round it up, because that's a 9. And we get 62.1. Anybody have any questions so far? Okay. Okay. Let's go ahead and add the following measured numbers.
104.409.
Yep, that's what the calculator would say. And what would be the rounding? Anybody can.
104.41.
So we're going to round to what place?
One's tenths.
Tenths. You got it. Perfect. And so we'll round to the tenths. And that digit right here, that's a 0, so we don't have to worry about it, do we? So we'll end up with 104.4. Okay. And again, that's because we're going to round to the tenths place, right? So. All right, let's go ahead and talk about prefixes. So in the metric and SI systems of units is where you're going to see the prefixes most often. Technically, you can put prefixes anywhere all the time. Okay? For example, you've all used prefixes all the time in your life and you didn't even realize it. If I want to get paid 100K, what does that mean? 100,000. Why is it 100,000? Okay?
Because of the K.
Yeah, what does K stand for? Kilo. Yeah. I'm technically saying I want to get paid $100 kilo. That's actually what I'm saying, isn't it? Yeah. And so I'm actually using prefixes. Prefix is the kilo, kilometer, kilogram, right? Yeah. And so we're actually seeing that right down there. And again, that means a kilometer is 1,000 meters, isn't it? This is the prefix. This is the unit. Okay? Okay. Here's millimeter. Milli like millipede or millennium. And so this is 1/1000th. So for example, there would be 1,000 millimeters in a meter. Or another way of saying that is 1 millimeter would equal 0.001 meters. Okay. This is some of the more common prefixes. I would very much recommend you memorizing them. First off, they're all around you all the time in your life, and you just have been walking oblivious through it and sometimes getting taken advantage of by it. Okay? So, yes. Like, for example, when you're buying a hard drive, which has more, 500 gigabytes or 1 terabyte?
1 terabyte.
1 terabyte. Why?
Because the terabyte is 10 to 12.
Yeah, it's this one right here. Yeah. So tera was a prefix, wasn't it?
Yes.
So was giga. And so there's 1,000 gigabytes in a terabyte, or another way of saying that is it's 10 to the 12 bytes. By the way, they also play games with units. Anybody get their internet connection? What's that measured in?
I think. Think
Megabyte?
you mean like when you're downloading, or just how it normally flows? Because for me, when it's downloading, it's megabytes, but when it's just normally flowing, I have no idea.
Yeah, so if you see the ad for your internet connection, like Spectrum,
No,
they-
gigabytes.
it's measured in gigabits, or it's measured in megabits, not bytes.
Bytes of storage.
Oh, yeah.
No, 8 bytes or 8 bits are a byte. They literally are just using bits a little bit because of history, and then they've kept it that way, and kind of intentionally, because it makes the numbers look a lot bigger, and so people are happier with them. But that's why, like, if you look at the advertised speed for your device versus the download speed, like you're downloading a movie or a game or something, just like you're saying, the download speed's in bytes. Yeah. And so your computer will give you bytes because that's actually useful for you because it's like everything else. If you ever want to compare them, by the way, you just have to take the internet advertised speed, divide it by 8, and that should give you something pretty comparable. Yeah. It's not going to be perfect because your computer also is an issue, right? But so like this is something you're seeing all the time. So a mega byte or megabit, that would be right here. That's that capital M. That's 10 to the 6th, right? And so there's a million of those if you're talking about the difference between a mega and a terabyte. Okay. Then we have kilo. This is actually a lot easier to remember than you might think. And that's because they're 10 to the 3rd steps, right? So each one is 1,000 times lower than the last. Okay? Or if you start at the bottom, they're 1,000 times bigger. Okay? And of course, you can do that with everything. You could do a terasecond. You could do a gigameter. Yeah. You could do gigadollars, gigawatts, right? You probably see gigawatts fairly often in the news and stuff. Anybody ever heard of a gigaton? Anybody ever seen any coverage on global warming? Yeah. Very common unit in global warming. Funny enough, global warming conversations are somewhat intentionally opaque and made so. And you'll see them reported in every unit you can imagine. So they'll be reported in various different prefix tons. They'll be then reported in metric tons in the same report. And then reported in meters cubed in the same report. And it makes it impossible to actually compare these things. You go on a website with data listed, and you'll see them 3 or 4 different ways, which is a real problem in the field, actually. It's becoming a disaster in and of itself. Anyways, the kilo is actually kind of unique, by the way, because it's the only lowercase one that makes things bigger. Okay? Now, these ones are the ones that are the smaller prefixes. So, like a deciliter is 1/10, right? There's 10 deciliters in a liter. If we look at centiliter, it's going to be 1/100th, right? Okay, that's like centimeter or century, right? Anybody know what decimate, like decimal, right? 1/10 of something? Or decimate? You reduce something by a tenth? All right. Milli, like millennium. And so we can have like a millisecond. Micro, this right here that looks a bit like a U, like a cursive U, right? This is actually mu. Okay? It's a Greek letter. Mu. That's the English equivalent, mu. It's a Greek letter. So you'll see people write basically cursive U's all the time for it, and that's fine. It's very hard to insert the Greek letters whenever you're like typing and stuff, so people just ignore it. You can also use MC and then whatever. MC standing for micro. Okay? And you'll see that a lot in like medical reports and stuff. Be very, very, very careful if you ever are doing things where people are quickly writing out things that could be micro or they could be milli. Okay? I've actually had a nurse, actually several nurses approach me after they'd taken my courses and been like, thank God you taught me about this, Dr. Clausen. And I was on training with another nurse, and the doctor wrote out really fast. And apparently they wrote out microgram, but they had loops on the top. And so the nurse that was training went, okay, we need to give this person a milligram dose of morphine. So 1,000 times the dose of morphine. Anybody know what that would do?
Kill you.
Oh yeah. Oh yeah.
And then she'd be fired.
Yeah, almost immediately kill them. Yeah, it would have been really, really bad. And the sad part is, I have been told that same thing by more than 4 nurses, and I know somebody that a nurse tried to do that to them. And they looked over at the machine as they're trying to set it. They're like, why are you pushing that so many times? No. Let me see the note. No. Get me somebody else. Yeah. Yeah, it's, I mean, it's partially the doctor's fault, it's partially the nurse's fault, and it's partially the system's fault, right?
I asked just to make sure.
Yeah.
Like, what is this?
Yeah. That's one of the reasons we double up the training, right? Everybody knows about milli and micro. And it kind of puts checkpoints along the way. Yeah, it's medical malpractice is definitely a thing. Nano. This is, by the way, anybody ever heard of microbiology or microprocessors? Yeah. So microbiology and microprocessors are both named so because they are micrometer in scale. Okay? And that's where they get the name. Micrometer. Nano. Anybody heard of nanobutts? Nanoparticles? Okay. Those are measured in nanometers. And so they're named after the nano right here, which is 10 to the negative 9. Or another way of saying that, there's 1 billion nanometers in a meter.
Yeah, I thought nano.
Pico. Anybody heard Pico?
No.
Did you say Pikachu?
Pico de Gallo.
Pico de Gallo?
That's the only one
Yeah.
I know.
Unfortunately, this is not something most people would encounter. This would be like picometers would be measurements that you take for like bonds. Atom molecules bonding.
Okay.
Yeah, super, super small.
So that's something like a rocket scientist would have to use, or?
More like a chemist. Yeah. Picoseconds is something that like would be speed of light sort of stuff. And like you can talk about picometers when you're talking about like the newest chips. So they've started trying to make experimental chips, computer processors, in the picometer scale. But it's really difficult because when you get down to that scale, particles just like pop out of existence and pop back into existence in a different place. So when you make a computer chip like that, where the circuits are that scale, you start having electrons that are in one circuit just pop out of existence and pop into existence another circuit. So such a processor could be like 1 + 1 = cat, because it could be a totally different process, right? So it's just a weird thing. Anyways, the world is not like you think it is once you get down small enough. Okay, let's fill in the blanks. Also, go ahead and get out your cards, because I'll scan everybody in. And one of the things I'll be working on this weekend, by the way, in case you're curious, is I'll actually be working on incorporating the plickers better into my shows. Yeah. Unfortunately, I'm having some issues. Okay. All right. So, 1,000 meters. What sort of prefix should you use for that to be a 1? Kilometer. You got it. Kilometer, right? Okay. 1 × 10⁻⁶ grams. Micro, exactly. Microgram. 0.1 liter. Deciliter. Perfect. Absolutely perfect. Okay, we are going to call this, let me get out my phone. We're going to call this A. So if you want to get this one right, you'll want to answer A. Please move your hand. Thank you. Fantastic. And if your name shades and lights up on there, you're good to go. Oh. Thank you. There we go. Okay. Did I get everybody? Fantastic. Okay. Now, all right, so we're going to talk about some measurements and length measurements. So here we see the length, the measurements, and their equalities. Does anybody know what an equality is?
Yes.
Yeah, it's exactly what it says on the tin, right? It's an equation, so this equals that. Or another way of saying that is it's things that are equal to each other, right?
The lesser than and greater.
No, this is just straight up equals to.
Oh. Okay.
Yep. So 1 meter is, by definition, has to be equal to that. Okay? And these equalities here, these ones are all going to be exact numbers. Because by definition, those prefixes, you have to have 10 decimeters in a meter, right? Can you have 11 decimeters? 10.1? No. By definition, 10 decimeters to a meter, right? Okay. So this right here is measuring volume. So we have the cubic centimeter, or cc, and this right here is 10 centimeters on each side. That's a decimeter, right? So if you took this cube, does anybody know what that volume would be? It is 1 liter. That's actually a liter. So a liter is actually a decimeter cubed. Okay?
So volume is height times length times width, right?
You got it.
Okay.
Yep, you got it. And so if we do that, 10 times 10 times 10, that would be 1,000. And that means there is 1,000 cc's, cubic centimeters, within that. Anybody ever heard a medical show? Hurry, stat, 1,000 cc's, or 10 cc's, or whatever, right? Okay.
Defib, right?
Huh?
Is that for like the defib?
No, that should be for, so that's actually, they're trying to do it for the adrenaline. But every medical show actually does that part wrong. So you get like this confusing jumble of terminology that just shows up.
Okay.
Like the defib is actually very rarely used. It only helps on very specific purposes.
Yeah.
Otherwise, it actually is completely counter helpful, and like using it every time would be a terrible idea. And like, because you can't do the chest compressions, you can't do any of that stuff while the defib's in use, right? And then you're electrocuting the poor person when you use defib.
It's going to stress them out more, which is most likely to just kill them.
Yeah, so what the defib's supposed to be used for is if you have your heart not pumping in the right rhythm, you can sort of reset that.
Yeah, it starts to spasm, and what it does is it shocks it back in.
Yeah. Very, very basic explanation, but
Yeah, a defibrillator, it does not restart a stopped heart. Once your heart stops, that's it. You're just done. There's no
no.
restart.
Chest compressions can restart.
Well, okay, but defibrillator can't. The defibrillator just shocks it to gain back in the right rhythm.
And
stops.
what the biggest thing that they use to actually restart a heart is adrenaline shots. Adrenaline shots are very useful for that. And that's where the CCs come from in those situations. But they always do it wrong in the shows, right? Anyways, when they're referring to CCs, that is 1,000th of a liter. Is there another way we could represent that? That's a milliliter, isn't it? Yeah. A CC is a milliliter. A cubic centimeter, or a centimeter to the third power, right? Cubic centimeter, which is a milliliter. Okay. It's funny actually because hospitals sometimes have like wrong batches of stuff sent to them, or sometimes their manufacturers change, and they change what SKU it is, and so sometimes the hospitals will actually get ones that say milliliter on them instead of CC, or vice versa. And it can sometimes cause real chaos. I've actually heard some really funny stories about that, where like for a week, all the nurses thought that they didn't have any syringes that could be used. Because they all said milliliter on them instead of CC.
Ours, we have to put on both sides. We have to put CC and milliliter now.
Mm-hmm. Yeah, that's typically what's done, but sometimes that doesn't happen, or they change manufacturer. Yeah. And that's literally just so that that doesn't happen, right?
Yeah.
Which is pretty funny, right?
We've had that issue before.
Yeah.
People didn't realize, like, no, just do the unit change. It's there.
Well, anyways, you all know now. So complete each of the following equalities. By the way, in case, don't get the wrong idea about nurses. Like, I just know all the bad stories about nurses. I know some good stories, but the bad stories are funnier, okay? And hopefully you all know that nurses do save lives like every day. Yeah, that's the thing. So please don't think I'm like anti-nurse. The reason I know all this, by the way, is all my former students always tell me all these funny fail stories. And my mother actually ran a rehab floor for like 15 years, yeah. So I had spent a lot of time around that. 1 kilogram equals what? 3,000, or 1,000, excuse me, 3 zeros. 1 CL. What's the CL stand for? Small c. If we get a CC, what is that? Yeah, centi. So this is a centiliter, isn't it? So centi is 1/100th, right? Okay. Fantastic. And so, by the way, another way to remember centi is cents. I have a cent. That's 1/100th. That's that same root word, by the way. They're all Latin root words, and they're Greek root words in all these cases. So, equalities, again, these are going to be 2 different units that describe the same quantity. These can be between units of the metric system, between U.S. units, between metric and U.S. units. You can have equality for basically anything. Okay? In this case right here, 1 meter equals 1,000 millimeters. Here we have 1 pound equals 16 ounces. These are both exact numbers because they are definitions. Okay? The ounces are defined based on that pound, right? So 1/16 of a pound, that is an ounce, period. Okay. This number right here, notice it has those decimal places like that. It looks a little weird, doesn't it? Okay. This one is not exact numbers. Okay. And that's because a pound is defined as something, a kilogram is defined as something else. And it's the measurements between those that actually gives you the conversion factor or equality. Okay? And so this one is not an exact number, but it's still an equality, okay? Just to break the pattern in your head in case it starts trying to form right now, decimal place does not necessarily mean that it is a measured number. Okay? Like, for example, we actually just did one here. That is a definition, isn't it? That one's a decimal place, but it also is a definition of what a centie is, isn't it? Has to be 100th, period. There's no error in that. Those are exact numbers. Okay? Okay. So the numbers in any equality between two metric units or between two U.S. systems are going to be definitions. Because the numbers in a definition always have to be exact, because that is how we've defined them, they do not have significant figures. That's not a concept. Okay? Or another way of saying that is they are infinitely significant. They have no error. And that only happens in clearly, very specifically designed situations. Okay? And so basically you have to define your situation in such a way for it to ever have an exact number. Right? Or another way of saying no uncertainty or infinitely certain. This right here is the case with, for example, a foot is 12 inches. That's a definition, right? Always has to be 12 inches. Okay. A minute is 60 seconds. Again, that's a definition. Okay. If you get 60 seconds, no matter what, it's a minute, isn't it? When equalities consist of two different unit types that have not been clearly defined, one off of the other, then you're going to get situations where you will have measured numbers. Okay? This happens quite a bit in the metric or SI units versus the imperial units, the US units. Okay? And so, for example, going from grams to pounds, 454 grams equals 1 pound. Milliliters to quarts, 946 milliliters equals 1 quart. So inches to meters, inches to centimeters, these all actually have are typically done in measured units. However, the foot actually has a actual defined off of the meter. That happened a little while ago, where the foot was actually changed to being defined off the meter. So that's actually 10 feet equals 3 meters. But people still use the old conversion factors, which are measured numbers. Okay? There you go. Anyways. Any equality can be written. By the way, if you're ever curious, the inch to centimeter, which is a very useful one to have, you can actually figure that out using your fingers. Okay? An inch goes down to about your bottom knuckle. A centimeter is the width of your fingertip.
I thought it was just an inch.
This is an inch. This is
Yeah. So if you go like that, you can actually go 2.5. It should be pretty close.
your hands. Everyone's hands are different sizes.
No, it's close.
Not like my elementary school. They taught me that.
We'll get out the inch measure sometime. We'll see if that one's right or wrong.
I'm gonna do that.
Yeah. It'd be interesting to find out, right? So any equality can be written as fractions. These are called conversion factors. You'll need to always include the units when you rewrite these equalities into conversion factors. So conversion factors are just taking one side of the equality and dividing it over. Okay? And that way you get both numbers in a numerator-denominator form, right? In a fraction. Okay, and so for example, 60 minutes is to 1 hour. you can always flip that around because anytime you have something, you can flip it, right? And that relationship still has to be true. So for example, 1 hour is 60 minutes. Okay, so this is where, and when we start solving problems with this, you're going to start catching me diverging from your book a bit. Your book likes to have very, very set, formalized things that you memorize formulas, and then you try to use those formulas. It's easy to teach. It's absolutely useless for you. Okay? You'll learn to answer problems on an exam, and you'll learn nothing else. All right? That's basically how math has been now taught in the U.S. and is being taught. And it is totally useless. Anyways. So I'm going to also teach you the methodology, which is that a more free flow, more understanding what you're doing with the math. Okay? And you don't need any formulas if you understand what you're doing with the math. And so you don't need to memorize formulas. For example, in my entire undergraduate degree, I maybe memorized 5 formulas total. Maybe. Everything else you can do by just canceling out units and understanding how to cancel out units. Why memorize formulas when you can just take the constant, cancel out units from it, and get the answers? Okay? And that's much, much more useful for you. For example, I ordered solar panels from China. I took care of all the shipping directly from the manufacturers. These are billions plus dollar businesses I was dealing with. Did all that. I did it right. There's a lot of conversions that have to happen to do that. Never had any problems. Never had any experiencing or getting anything through customs before in my life. And that was when they put all those like protecting U.S. businesses. Remember that? They put all those things against solar panels. That was right in the middle of that. Yeah, that was crazy. I'd have to refiguring them out like every couple weeks. It'd be like, it's to this part, rules have changed. Gets to this part, rules are different now. It was pretty crazy. But I saved my parents like $60,000. So, yeah. It was worth it. So anyways, these are some of the metric, length, volume, mass, time, and their equalities. These are the US ones. This is the metric to US. I don't really expect you to memorize a lot of these things. This would be a great place to use like notes for common conversion factors that you might need. For example, something to convert between like feet and meters or inches and centimeters, right? So in your problem solving, have I told you guys how you can solve all problems all the time? Okay. Let me go ahead and drop some like world-changing information on you. It's completely and utterly profound. Okay? You ready for it? Okay. Okay, so all problems that can be solved or can be incremented towards solving can be done so by this methodology. Okay? And every single test, every single study has found this increases your success by at least 80%. Right? So hugely successful. What do I have? Where am I right now? Okay? Number 1, expressly write that out. What do I have? What are my tools that I have? Where am I right now in this problem? Okay? Number 2, what do I need? Where do I want to be when I end this? Okay? And write that out expressly. And then number 3 is to state a pathway you think can lead you there. It's usually easiest to work backwards. So like if I want a specific unit at the end, I can work backwards from that unit. Okay? If I want to be a doctor in 10 years, then doctor is my goal. Where am I right now? college student at Cumberland University, right? And then I'd express my classes. I have these things that have been done. And then you would write a pathway from one to the other. Okay? And then you do your best to sort of try to get on that pathway. If you need to change the pathway part of the way through, you'd express that again. And so that planning really, really helps you solve any problem. Okay? It takes something that's very large, unmanageable. It breaks it into pieces, which are then manageable. Okay? Okay. Same thing in problem solving. So in problem solving, we're going to oftentimes have to do multiple conversions. Once you start getting to the fourth or fifth conversion, most of you start going to go, oh my goodness, I have no idea what's going on. I'm not sure if I'm going to be answering this right or wrong. Okay? And so you really want to break these down into a pathway, right? That way you always know once you cancel out your units along that pathway if you're going to be right or wrong. I know that I gave the example for solving chemistry problems, but it's actually a profound methodology to like solve life. Okay? So, yeah. Now, a doctor's order is prescribed a dosage of 0.150 milligrams of Synthroid. If you only have 50 period, what's that stand for? Micrograms. Yeah, it's micrograms. Tablets in stock. How many tablets are required to provide the prescribed dosage? This is an actual real-world problem, isn't it? That many of you will have to do at some point in your life, or if you have not already done, honestly. So let's figure this out. So first off, what do I have? Where am I at right now?
You're given
50
0.150 milligrams.
Yeah, I have a 0.150 milligrams of Synthroid that I'm going to be requiring, right? Now, you can list this 50 microgram somewhere under given as well if you want to. Okay? I have a 50 microgram, and it's a per tablet. But it usually is better to put this onto your pathway, your connections. Okay? And you might end up moving that over to pathway or connections later. You can do that. Because what you realize once you start writing this down is that when you have something that says 50 microgram tablet, that means that's 50 micrograms per tablet, isn't it? Or divided by tablet. Okay? And so that is actually an equality, isn't it?
Yeah.
Yep. So that is 50 over 1 tablet. Right? Okay. Does that make sense? So you can represent that as an equality. 50 micrograms equals 1 tablet. You can represent that as a conversion factor as well. Okay? And if this is true, then the flipping them upside down is also true, isn't it?
1 tablet is 50.
Yep. And so this really helps me out because now I have things that I can connect a lot of different things with. The next part I do is, what do I need at the end of this? Well, I need a number of tablets, don't I?
Yeah.
Okay. And so I need my number of tablets there. All right. So I typically work backwards. But I'm going to work this one forwards, and then I'll work it backwards later, okay? And you can decide which one you like. Okay. Do you guys want me to work it backwards first?
Yeah.
Eh? Okay. So working it backwards, you start with, what do I need? Okay, where do I want to end at? And I want to end at tablets, don't I? Okay, so I have tablets right here. Well, what is related to tablets and going to get me somewhere closer to being what I have right now, which is a weight, right? It's a mass. Yeah, this right here, isn't it? Yeah. But it's not the right way, is it? I want to end in tablets because tablets is on the bottom. So I need to flip that. 1 tablet is 50 micrograms. Okay. And so I go from tablet. I can go there. Okay. Now, let's see. Micrograms, that is not milligrams, is it?
Now you have to make them.
Yeah, so I need a conversion factor to go between them. And so I want to cancel out the milligrams. I'm going to need that on bottom, aren't I? Yep. And I'm going to need to get into micrograms, which will end up canceling later over here. Okay? And so I'm going to go micrograms. Okay. And then how are those related to each other? Okay. Now, I personally prefer just relating all prefixes back to the base unit. Okay? So for example, if this was me doing this, I would go, how many of these are there for a gram? Yeah. And I just put that in both places. So micrograms, there's 10 to the 6th of these for 1 gram, right? Milligrams, there's 10 to the 3rd. Okay? And I can simplify from there if I want. Okay? Yeah, so 10 to the 3rd on the top. Yeah, I just take this number and... no, I take this number here and subtract it from that. If you do that, you can also just step back. 10 to the 6th is 1 million. 10 to the 3rd is 1,000.
Yeah.
And so 1 million divided by 1,000.
So subtract the bottom line from the top line?
Yeah, if you want to save time mathematically, the exponent on the bottom of the division is subtracted from the top.
Ooh, are we gonna have computers do this for us?
You can.
Well, you can also
In the
just
hospital?
you can also just move the decimal over and then divide it out.
Yeah, the other way to do this, and this is how I'd recommend this if you're having difficulties with exponents, is just writing the whole numbers out. So 10 to the 6th, that's 1 million. 1 million, and then you can use a calculator if you want, divided by, and then 10 to the 3rd is 1,000. 1,000. Okay. Okay, so we get 10 to the 3rd at the end of that. Now, that right there is the next step I need to do, isn't it? Now I'm going to be in my milligrams, aren't I? I have to deal with milligrams somehow. And so what number had milligrams? That one right there. Yep. And so when I now go ahead and put this in the calculator, I just go backwards. That's it. I have my plan. Okay? Now, the nice thing about going from what you need to what you have instead of what you have to what you need by working the problem backwards is I'm always the correct unit on the top. I always end up in the correct unit. I don't have to go through and flip things because I messed up. Okay? Okay. Let's look at if we go forwards, okay? So we write out 0.150 milligrams of Synthroid, right? Okay. That's a weight. What do I have that can get that into tablets eventually? I have this relationship, right?
The micrograms.
Yeah. Yeah, I have that micrograms of Synthroid per tablet, don't I? Okay. And so somehow I need to get that number into micrograms, don't I? All right. And so what I'm going to do is I'm going to write out my 0.150 micrograms of Synthroid. I'm then going to take and I'm going to use an equality or a conversion factor, right? And what I'm going to do is I need to get rid of the milligrams, so milligrams needs to be on bottom. I need to go into micrograms because that's my next step, is going into micrograms. And so the micrograms is on top. Once I have that relationship expressed, then I can go ahead and go, well, there's 1,000 micrograms for every 1 milligram, right? Okay. Okay. And you don't have to work it out in place. You can work it out to the side. For example, this has been worked out to the side. See that? Okay. Now, once I'm in my micrograms, I can then use that 1 tablet is 50 micrograms, right? And so I set up my, again, conversion factor. I'm going to use this one in this case. And I'm going to place it down here. And again, why do I know that works? Because I'm going to just sit here and cancel out my units each step. Okay? So every single step, you should be canceling out 1 unit and going into something that gets you where you want.
Like stoichiometry?
This isn't stoichiometry yet. This is typically called something like dimensional analysis. Yeah. Or unit conversions. Yeah. But it's very, very similar to stoichiometry. And honestly speaking, stoichiometry is just unit conversions. Like, almost all the math we do in this class is just going to be pure unit conversions. Okay. If you understand the unit conversions well, and you can work them out just 1 step at a time, the math in this course will become very, very, very trivial. Okay? Okay, so I end up in 3 tablets, by the way. Now, this is kind of a weird number. If you're not cutting tablets at all, you just have to round it up. But if you're breaking apart tablets, you can have part tablets. So, but in this case, 3 tablets, that's good enough. Okay? Notice it is expressed in this case as if it's an exact number. Okay. Because we're using whole tablets. We're not allowing people to change them. Anybody have any questions about that so far? Okay. Okay, so remember, the most important thing about the math in this course and in this course in general is that to take complexity, break it down into parts, and solve each single part one at a time. Okay? Always just break things down. If it seems hard, if it seems complex, break it down into parts. If your pace on a treadmill is 50 meters per minute, how many minutes will it take you to walk a distance of 7.5 kilometers? No, unit conversion, isn't it? Okay, so how do you solve all problems? What's up? Why are we on the last one or this one?
I don't know. I've never figured this out.
Okay, so how do we go with this one?
We find out what we have.
Yeah, so what do we have? Well, we have,
We know the distance is 7.5 kilometers, which is 7,500 meters.
yep, yeah, you could do conversions if you're comfortable with them right off the bat, but
And then just apply it.
yeah. So 7.5 kilometers, that's what we have. And then what do we need? We need time, right? How many minutes? Okay, so somehow we need to go from a distance to a time, don't we?
So we're walking 65 meters
Yeah.
per minute
Uh-huh.
on the treadmill. Okay.
Yeah, 65 meters per minute. So next thing we want to do is figure out a pathway from one to the other. Okay? Now, we're wanting to go from kilometers into time, right? This right here relates distance to time, doesn't it? We just don't have the right units yet. Okay? So we have our relation between these two things, which is that speed, right? We just need to fix the units. So how do we fix the units? We go from the 7.5 kilometers, right? Anybody ever seen railroad tracks before? Okay. Railroad tracks, the stuff on the top is multiplication, stuff on the bottom is division. Okay? Just a faster way to write it out, because you can use the line in your paper as this middle line. Okay. Is everybody okay with me using that? Am I confusing anybody? Okay. So everything on the top is multiplication? Okay. So I'm going to need to get into meters, aren't I? So on the bottom I need, that would, if I put meters here, would that cancel this over here? No. To cancel the kilometers on top, I need kilometers, don't I? Okay.
Oh, I thought you
Okay. And on the top here, what do I need? Meters, right?
Meters to
Yeah. Yeah. Okay. And so what relates those two things? That's that prefix, isn't it? Yeah. So how many meters are there in a kilometer? 1,000. Got it. Okay. So I now cancel out units, and I go, okay, I've canceled out kilometers. I'm in meters now. Is there something that relates meters in the direction I want to go? The speed, right?
Yes.
Yeah, that. Right there. And so I go ahead and go, okay, I want to get rid of meters. So meters has to be on the bottom. Got it. On the top, what do I have to have? Minutes, exactly. Because that's the relationship I'm using here, right? That's that conversion factor. And so I go ahead and start filling in the numbers now. Anytime you see a divide by, what's on the bottom? 1. Yeah. Everything's divided by 1 if it's not stated, right? Yeah. And so on the top, before there was a 65 meters. That 65, that meters and 65, those have to move together, right? Because a number and unit, those are a unit, right? Those are a totality. Okay. This is a place where people have difficulty and get tripped up quite often, by the way, is they'll try to put the 65 on top even though they moved the minutes up there now. Because there isn't a connection all the time between unit and number being one thing. Okay? Okay, and so now I go through and I can cancel meters, right? Fantastic. I'm left in minutes now. Is that what I wanted?
Yeah.
Yeah. There we go. Having worked in a facility before, you can very clearly see this is like something you do all the time in like shipping and handling and packaging.
Yeah.
Yeah.
Yeah, so the fastest way to do this, you know that, so it depends on what it is. It's going to either be 115.38, but if it wants it in exact minutes, because 380 you can't have, you could technically have it, so it's either 116 or 115. I made 7.5 kilometers. I know times 1,000 makes meters, so 7.5 times 1,000.
Yeah.
is 75
Okay, so 7.5 times 1,000, of course, 7,500. Then we divide that by 65. You can use a calculator. I, again, very clearly said scientific calculators are a thing. I don't require you to have a slide scale in your head.
They're on sale on eBay right now for $15.
Yeah, they're cheap.
What?
I just got one from eBay this morning
The TI 83 Plus?
for 15
I
bucks.
just got mine for like $80.
Yeah, that's why the syllabus said eBay.
I looked, I couldn't find anything. It was gonna
Really?
take like 3 weeks.
Oh, wow.
When I found, yeah.
Anyways, so yeah, do that in the calculator. You should get like 115 or something, was it? If you're doing the calculator.
115.38.
Okay. Yeah, and then it's only 2 significant figures because of the kilometers right there. And so we just put 120 because we round that up to 120. Okay. Does anybody have any questions about that? Okay. All right. Fantastic. Densities. Let's compare the mass of an object to its volume. The mass of the substance divided by its volume. It's defined as your density right there, which just says what I just said. Substances that have higher densities typically are going to be more mass packed into less area, right? If it's the same material, then that would mean that they have more particles packed into the same area. Okay? Lower densities are going to contain particles that are farther apart. Now, I know your book just outright says more dense means more particles packed in tighter, and period, with no qualifiers at all. That's not actually right. Some of like the metals versus the non-metals have the same crystal structures, same structure. Particles are packed the same distance. but the metals just have higher atomic weights, right? And so they're just more dense. Okay? It's something I don't know why your book says it like that. It's just not right. But anyways, like they partly right, but not quite. So metals like gold and lead typically have higher densities because their atoms are packed closely together. You were at my desk before. I have a cool silicon, right? Not very dense, is it?
No.
Yeah. It looks like a iron ingot, right?
Yeah, I thought it was aluminum.
Yeah, it's pretty wild. Whereas tungsten, on the other hand, is super dense. I could give you a small CC cube, and I'd throw it to you, and you'd end up like on the ground because you'd be surprised. It's so heavy. Anyways, these are some different densities right here. As you can see, water has a density of 1. It's actually called specific gravity of whether it will float in water, but it's based off of density. Okay? And so, for example, cork floats on water because it's less dense than the water. Ice floats on water because it's just a little bit less dense than water, liquid water. On the other hand, metals almost universally more dense than water. Okay? This right here is some different densities of common substances. How am I doing for time, by the way?
You got about 8 minutes.
8 minutes? Okay. Anyways, these are some various different substances. If you ever wondered why you go to the pumps for gasoline and you see the puddles have like this film on them, that's the gasoline. Yeah, the gasoline's less dense than the water.
I thought aluminum floats in water.
No, not a ingot of aluminum.
Okay.
So what happens is we can talk about boats if you guys want. We'll just sort of finish it up on boats and we'll start on specific gravity later. I usually wait for specific gravity, but it doesn't matter. Basically what you're doing when you're making a boat is you're mimicking it as if it has more volume. Okay? And so you spread the metal, the surface area out, and then put some lips so the water can't get in easily, right? And then that mimics the same sort of thing that would happen if you had more volume, right? Yeah. And you could do very similar calculations. There's a bit of a compounding and a bit of factors that can play into that. That'll divide that a little bit if you're going to be starting building big ships. But it's a pretty good mimicry for just mimicking density. So spread the weight out more. It's as if you're less dense, right?
Because I figure if you crumbled up a ball of aluminum and dropped it in water, it floats.
So if you crumble it up tight enough, it won't.
Okay, so I assume that's what it's talking about. Like if I just took regular and just crumbled it up without like pressing it and everything,
Yeah.
it would float.
Yeah, if you just crumble it loosely, it's going to have a bunch of pockets of air in it.
And the air is less dense than water.
Exactly.
Okay.
Yeah.
That makes sense because I was like, that was one that was throwing me off for a second.
And in fact, a lot of those cars play a similar game where they have like pockets of air surrounded by material.
Yeah.
And then they can float for small periods of time on water. Yeah. Pontoon is the same thing. Pockets of
Yeah, it's
air.
like a pontoon. A lot of times a pontoon is full of air anyway.
Mm-hmm.
I had a pontoon, so like you wouldn't have a hole like that caused issues. So like we understood that you have to get the air because it's less dense.
Yep.
And then it outweighs it because the density of the air is so much less than water. Even adding something like aluminum still counteracts it when it's high enough.
And like balloons are the same thing. If you fill a balloon with helium or hydrogen, it'll float in air, right? But if you fill it with something heavier, like air from your lungs, it doesn't float. It just drops down.
Yeah, I forget the one that makes your voice deep.
Probably nitrogen. Helium would make your voice like chipmunks.
Yeah, it makes it
Yeah. It usually would be a heavier air that'll make your voice deeper. Yeah. Technically, you could do xenon, but that would be really expensive.
I'm a college student. I'm bored.
I definitely don't have the budget for xenon.
I go to work and I'll work till midnight tonight, and then you drive an hour and a half home. That is my stuff.
Okay, folks, did anybody have any questions they want to ask?